Okay, I'm here to help you with assignment 2. So I encourage you to watch the 35-minute introduction video that is a good summary of all the topics we're covering this week. And that will help you to answer some of the first 5 questions, multiple choice questions. But let's work on number 6. So take a look at number 6. You'll have different numbers than I do, but I'm going to solve it not using any numbers. So the first thing I'm going to ask you to do is to pause the video and look at number 6 and draw a figure that shows all the relevant information and the electric field vectors. So pause the video and do that. Okay, check your figure against mine. You should have 2 charges, and I drew them different sizes because they're not equal. And in my case, Q1 is bigger than Q2. And so Q1 has a field going away from it. So I show, remember, we're calculating the field at point P. Whoops, I forgot to mark point P. So there's point P, and I drew E1 in this direction because it's the field due to Q1. And so it's going away from Q1. Electric field always goes away from a positive charge. And if Q2 is positive, then E2 is this way. If Q2 were negative, E2 would be positive. So notice we have 2 positive charges, but we have a positive and a negative field. That's why it's important to draw the figure. So I marked out this distance D, so I can solve it for any D. And the distance, the important distance, is the distance from the point to the charge, because the field here is going to be K Q1 over R1 squared. And then this vector, E2, is going to be K times Q2 times R2 squared, which is also D over 2. So now, using the figure, it's really important to draw the figure. I can't emphasize that enough. Now, using the figure, what you want to do is write down the equation that you're going to use to solve the problem for what the field is. So write that equation down and then come back. Okay, this is what you should have written. And notice the formatting. You want to practice this. And I urge you not to just watch the video, but to write down everything I'm doing, just so that you're getting the practice of actually doing all the steps. So the total field at point P is going to be the sum of 2 vectors. And this is, I put the vector symbol over these, and I put the plus sign here because we're adding vectors. I haven't put the direction in yet. But when I write the equation out, E1 is going to be KQ1 over D squared, and it's positive. Why? Because I know that from the figure. Then I put a negative sign here, because the field due to Q2, although it's positive, the field is in the negative direction. So I write KQ2, the distance is the same, D over 2 squared. And so that, since I've accounted for the direction, the sum of those 2 factors times I hat will be the direction of the vector. And in my case, since Q1 is bigger, I know that E1 is bigger, and the answer is going to be positive. But one thing worth noticing, if Q1 were negative, then this would become negative, which would be correct. If this were a negative charge, then E1 would be going towards it. And if Q2 were negative, then E2 would be in the positive direction, because field lines always go toward a negative charge. And so this equation will work, actually, whether the charges are positive or negative. It'll automatically adjust the direction. So this is the general solution for any problem of this type. Okay, the last step is to finish the algebra, so go ahead and do that. I'm going to pause the video. You pause and do the algebra and get the final answer. Okay, I did the algebra in one step. When you square the D over 2, you're going to get D squared over 4. And that 4, when you do the compound fraction, ends up in the numerator. And so the 4, the k, and the d squared are common to both vectors. And all that's left behind is the q1 minus q2. And I forgot the I hat. So there it is, the I hat. So this is the general solution. This will actually work for the problem where you're at the midpoint. And it'll work for any positive or negative charges. How do I know that? Just by testing it. Okay, that's problem 6, finished. Okay, the general method that we just did can be used for lots of problems, even more than 2 charges, or not necessarily in a straight line. But take a look at number 7 and see if you can draw the figure for number 7, and then come back and check at what I have. Okay, this is what your figure should look like. You have the 2 charges. I don't know the numbers you have, but my numbers, the Q1 is bigger. And so the separation of the charges I call D. You could give it any name you want, but you should give it a name. And then the distance from the point to Q2, since it's on the right of Q2, I just called X. You could give that any name, but it should be different from D because those distances aren't the same. And then I label my charges. Check your figure, make sure you have all this. Label a point P, fill in anything that you forgot to put, and then I'm showing the 2 vectors. These are the 2 vectors I want to add. And notice, I didn't mention this last time, but the only vectors I'm showing are the 2 field vectors that I want. I don't have any other vectors, no force vectors over here or no field vectors over here. We only want to know the field at point P. This is an important concept, and so the field here is due to the field due to Q1, due to the field due to Q2, and oops, I can see I already made a mistake because Q1 is further away. That vector should be smaller. So I wasn't thinking, I was thinking like the last problem. So, and notice, even in this problem, if this were a negative charge, then that vector would turn around, and if this were a negative charge, this vector would turn around. So now do what we did last time. Write the equation for E at P for this situation. Write that equation and come back and check against mine. Okay, there's the general solution. And it works. If Q1 is negative, that will make this negative, which it should change the direction, and the same for Q2. And what I didn't mention last time was you got to be sure when you put the numbers in to calculate this that you use meters. And since K has 10 to the 9th and Q is in nanocoulombs 10 to the minus 9, when I calculate it, I usually don't bother writing 10 to the 9th and then 10 to the minus 9 because they cancel each other out. So you can just multiply, and I use 9, not 8.99. I use 9 for K, so you just multiply 9 times the charge value plus the sum of those 2 lengths in meters and square it, and then add that, and you should get the right answer. Okay, 8 and 9 are problems with finding the electric field to 0, and I'm pretty sure there's a video on that, so I won't cover that, so I'm going to jump ahead to number 10. Take a look at number 10, and in this case you're adding 3 vectors. So draw out the diagram and show the vectors, and then we'll do the problem together. So do the diagram. Okay, so notice a very similar formatting. I drew the 4 charges equally, 3 charges and a point equally spaced. I labeled all those distances D because they're equal. I put down the value of the charge, -1, +3, -4. I labeled the charges. So Q1 is negative, so E1 is toward the negative. The field at P is going toward the negative charge, right? The field due to this is field lines going in. And this is positive, so the field goes out. So E2 is going in this direction, which is positive. And then Q3 is negative, and so the field goes toward the charge, and so it's negative. So I have to add these three vectors. So write down the equation that adds those three vectors. Okay, I want to emphasize again the importance of writing all this out. So just getting used to writing it out. So the field at P is the sum of three vectors at P due to the three charges which have fields that act at P. And so E1, the field at the point due to charge 1 is going to be K times that charge, negative 1Q, divided by that distance. That's a distance of 3, so 3D squared, plus E2 is positive, so that's K times the charge, 3Q, divided by the distance squared, 2D squared. Oh, I should have parentheses there. And then finally, the last one, since it's a negative charge, the field is negative, and so K times the charge 4Q, now the distance is just D, so D squared. And so I can factor the K, Q, and D squared out of all terms, and that leaves behind 1 over 3 squared, 3 over 2 squared, and 4 over 1 squared. The 1 is squared, the 4 not. Yeah. And so you have a negative 4, a positive 3/4, and a negative 1/9, and you get a negative 3.36. And that's the answer to 10.